Okay, so let's take a look at a hash table. A hash table is a data structure that stores unordered sets by mapping each item to a location in an array. The key advantage of doing this is that searching for an item is O1 on average. And a hash table is just one way we can implement a set ADT. Let's get a little more insight about why this is going to be good. Okay, so the problem with lists and arrays is that the item we want could be anywhere in the list or array, right? When I insert like number 3, let's not do that one. The number one into this array, then the number 1 could actually be at any position. And since I don't know which position it's in, I have to start at the top and walk my way down. And then, I'll finally find it at position 5. Or if I was looking for 17, I would have to start at the top and work my way down. And eventually I'd find it at position 9, right? And so storing things in a list and arrays without any kind of organization or meaning behind it means that it will be very inefficient to find the data we want. We don't know where to look, and so we have to look everywhere. So that's bad. That means in the worst case, right, we have to search the entire length of an array or list. So the alternative would be to not have to look everywhere, right? To pin down the number of spots where an object or an item could be to only one location. And if it can only be in one location, that's the only place we have to look. It's just like when you organize your bedroom, right? You put everything in a certain spot, and then when you want it, you go straight to it. You don't have to walk around your room looking for what you want through all of your other possessions. If we did that all the time, we would all go insane, right? Maybe some of us live that way. I have at times, perhaps. But if you organize things properly, it's not hard to find things, right? We know that intuitively. And so we need to achieve the same simplicity in the data structure. So what if we restrict where we put items? Here's an example. What if the only place I'm allowed to put an integer is in the spot in the array that's equal, whose index is equal to the integer modulo 10? So if that modulo bothers you, just remember, when you modulo by 10, what you're basically doing is dividing by 10 and taking the remainder. And when you do that, you're just pulling off the last digit. So 14 modulo 10 is 4 because it just pulls off the last digit. So the only place I'm allowed to put 14 in this array is in position 4. That's the only place. That's the only place it can be. So when I want to find out, does my set have 14, I just go straight to position 4 and I check it. If it's there, I've got 14 in my set. If it's not there, I don't have it in my set. It's that simple. And it's a single operation, right? Because I just need to do the modulo and a lookup in the array. And well, really that's 2 operations, but big O of 2 is big O of 1. So this is constant time and efficient. All right, so this is the key idea, right? If I wanted to know if I had 99 in my set, I would do 99 modulo 10. That would be index 9. And I would say, no, I don't have 99. But if I wanted to know if I had 2, then I would do 2 modulo 10, and that would give me index 2. And then, sure enough, the number 2 is in my set. So I can use this logic to very rapidly determine where things are and verify, is it in my set, is it not in my set, and even insert it in the set if I choose to. So here's how inserting an item works on a hash table. You calculate its index, and in our simple scheme right now, we're just inserting integers, and we just modulo them by 10 to figure out where we should put them. So I take 21, I modulo it by 10, that gives me the index 1. And in my hash table, there is no value 21 or any value. And so, in fact, I can easily insert it there. So I stick a 21 here at position 1. And so, right, I calculate its index, compare to what's already in the table. There's nothing there. And so since it's not there already, I can add it. If I want to remove an item, I calculate its index. I look to see, is it in my table? And if it is, I remove it. And so after I do a remove on 14, my set no longer has 14. Simple. Okay, and if I want to find an item, I calculate its index. I look to see if it's stored in the table at that position. If it is, I return true. If it's not, I return false. So here I take 66. I take a mod of 10 and find position 6. And there's nothing stored there. So that means 66 is not in my set. And so I return false to indicate it's not there, right? These are all very efficient operations. So why is searching a hash table fast or using a hash table fast? Well, we can calculate an index in O1 time. We can look up an array entry in O1 time, right? It's just a base address of the array plus offset. That's a single add. Then plus a load, that's a single operation. And then comparing two keys for integers, that's a single compare instruction in most processors. So that's like 5 or 6 instructions. And we only have to do those same 5 or 6 instructions anytime we want to find something in the hash table, as opposed to looking through an entire list. So that means that insertion, find, and removal can be done in O1 time. Okay, so this is extraordinarily quick. Now, I am oversimplifying it a little bit, and some of you may be wondering, what happens if you already have something in your table where you want to insert a new item? Okay, well, we have to deal with that. That's called a collision, and we need to take special measures to make sure collisions happen very rarely. But it turns out we can do that pretty well, and collisions aren't really, collisions are something we have to take care of, but they don't ruin the hash table for us. Okay, they're just something we have to deal with in a smart way. So a hash table is a data structure that stores unordered items by mapping each item to a location in an array. And because we know where to look in the array, we can find things quickly. What this means is that we can do searching, inserting, and removing on a hash table in O1 time on average.